All right, guys, happy new week. We are closing some things out. Listen, we're going to be starting from number 6 and working through a few more of the Cornell Notes that we did. So let's get this thing rolling. Previously, we learned that V stands for voltage. I is actually a letter that stands for current, and we measure that in amps. You've probably heard that before. Those of you that have looked around at your car fuse box or bought fuses, you know that they come in 30 amp, 10 amp, 15 amp fuses, depending on what they're providing power to. And then resistance we're going to measure in ohms. Now that came from a gentleman named George Ohm, German scientist, okay? And he found this relationship between the current and the voltage and the resistance. He actually did it while he was doing a demo in class. And this project was designed by Alessandro Volta, where we get the term volt. But here's the formula, and if you notice, it looks a lot like our distance and rate times time. So, to walk you through it, here's what we do. If we want to find voltage, we're going to multiply the I, current, times the resistance. Or, if we wanted to find the I, current, okay, we would divide the voltage by the resistance in the circuit. How about if we wanted to know resistance? Divide the voltage by the current. It works the same way as the other formula that we looked at earlier in the year when we were dealing with motion. All right, so let's take a circuit. Remember the plain old circuit. Okay, now if you look right far over on the left, I've got a 9-volt battery, when this snaps on top. And then where I see 1, that's a wire that goes to R1. Okay, there's a load. Okay, and let's just say it's a light bulb. Okay. Question, can we calculate the amps in this circuit using Ohm's law? Well, we're going to do it the same way we did distance and rate and time. Sure. Okay, let's 9-volt battery. Here's an itty bitty light bulb. Let's call it R1. R3 is a bigger light bulb. And R2, is a between the two. R1, in other words, resistance 1, resistance 2, resistance 3. Now look, they all have different resistance measurements. R1 has 3 kilo ohms. R2 has 10 kilo ohms. And R3 has how many? You got it. Okay, so there's our formula again. All right, so, do we know the voltage? Well, yeah. So that would be the number on top. So if we're trying to figure out the current, we have to know the total resistance. What is the total resistance in ohms on this circuit? Now look at the diagram and think about it. You're probably hitting the right number. 3 plus 10 plus 5. 18 kilo ohms, right? With a K in front. All right, regardless, we're going to divide these numbers. All right, so what do we get? Think about it. 9 is what part of 18? You got it. 0.5 amps or a half an amp. Now, the problem is a half an amp of power coming from a 9-volt battery with 3 lights with that amount of resistance. The truth is they're barely going to light up. That's not a lot of current. So how could we fix that? I mean, we might want to change the light bulbs or add more voltage. Maybe we're going to use 2 9-volt batteries, for a total of 18 volts. Or, we could reduce the type of batteries. LEDs would light up just fine. We're assuming that these would be like flashlight bulbs. Probably not going to light up that much at all. Okay. Now, the other factor, just like we calculated power before, is that's calculated by the current times the voltage. Power, current times the voltage. Voltage is movement. Current is movement. It's the amount, go back to our river illustration, it's the amount of water times how fast it's going. See, and you can kind of tie those together. So you may not, forget them. Now I'm just going to give you a heads up. The very last thing that we do is we're going to do a worksheet that you guys turn in where we're going to be messing around with this formula, playing around with it. It's very real scenarios that have come directly off a set of plans, or several sets of plans that I did in architecture. But the point is, power is calculated by how much is moving and how fast it's moving. The voltage times the current. Okay? It's how we calculate electrical power. The last thing I want to leave you with, real quick, is when you get electrical power from your house. Pause this, take a look at every single thing that's called out here, and look at all the pieces that bring power to your house. Over on the house, you've got that meter, the electrical meter that Tico has to read every month, right? And then all those power lines are brought in a pipe, and then it's got this weather head. It has a curved top like a candy cane. The electrical lines go in. They got a house hook that helps hold that line to the house. And I know one of our guys that has left Plant City is graduating from a different school. During the hurricane, this main electrical line got popped from their house, and they had no power for like a month. Okay, transformer. Okay, that's a big piece, and sometimes when it explodes, it makes a bodacious sound, right? And then you've got the power lines that come in. But I wanted to familiarize you guys with how electrical service is brought to your house, and we'll keep going in the next lesson.